Hello everyone, in today's video we're going to look at the concept of temperature and what a physical rigorous definition of temperature actually is. Now we all have a fairly intuitive understanding of what temperature is. It's the measure of hotness or coldness of a body. We expect that if we have two bodies, one hotter than another, then the temperature of the hotter body will be greater than the temperature of the colder body. Moreover, if we take these two bodies and we place them in what's called thermal contact with one another, which means that they are able to exchange heat with one another, then we expect that heat, which is signified by the letter Q, will flow from the hotter body into the colder body. And this matches with our everyday experience, right? If we touch something very, very hot, we burn our hand, and that's because heat is flowing from the very hot object into our hand. But moreover, what we expect is that once we have placed two bodies in thermal contact with one another, they will exchange heat for some time, and they will only stop exchanging heat once they reach the same temperature, which I write here as T subscript F for final temperature. And this is what's called reaching a state of thermal equilibrium. And more specifically, or more rigorously, a state of thermal equilibrium is defined when two bodies have the same energy content, and we expect that to happen when they're at the same temperature. But what is actually going on here? Because it seems that something irreversible has happened, right? We take two bodies at different temperatures, we place them in thermal contact so they can exchange heat, and they always end up in a state where they're at the same temperature in thermal equilibrium. But we never see the reverse. We never start off with two bodies at the same temperature, place them in thermal contact with one another so they can exchange heat, and end up in a situation where one is spontaneously hotter than the other. So we need to get a handle of what this concept of temperature is actually signifying and what it's all about. And to do that, we need to look at the concepts of microstates and macrostates. So what are microstates and what are macrostates? Well, let's suppose we have a big box of gas molecules, right? And each molecule in this box has a certain position and a certain momentum. So each molecule is one of these circles, and the arrow signifies how it's moving and how fast it's going. So a microstate is the specific information relating to this box of atoms which tells us the exact information of every single particle. It tells us exactly where each particle is and how each particle is moving. It is the most granular form of information we can get about this system. And as you can imagine, there are an almost endless supply of these microstates. They're not infinite, but they very well might as well be. Because if we were to just move this particle over a little bit and give it a slightly different momentum, that is an entirely different microstate, right? So a microstate tells us the most granular information possible about the system we are working with. In the case of a box of molecules, it tells us the exact position and momentum of every single molecule in that system. And now we have what's called the macrostate. Now, the microstate, although it exists, no one is saying that these particles aren't moving like that. The microstate itself is impossible for us to directly observe, right? Because there is way too much information there. And even if we could somehow measure the position and momentum of every single particle without interfering with the particles in any way, which is impossible, there is no way that we could actually use the microstate in any meaningful way. Because if you've got a system of 10 to the 20 particles, then that is way too much for any computer to process. So instead, the thing we actually work with, the thing which we actually use in our calculations and make predictions about, is what's called the macrostate. And the macrostate is defined by the macroscopic variables of the system which we can measure. So in terms of a box of gas, the macrostate will be defined by the pressure of that gas, P, the volume of that gas, V, the temperature of that gas, T, the energy of the gas, all these things which we are actually able to measure, which we can create an experiment to observe. And that is what the macrostate is. It is the macrostate is defined by the values of the macroscopic variables associated with this microstate. Now, unsurprisingly, because these are macroscopic variables, if we were to take, say, the pressure, for example, then we can imagine a ton of different microstates for every single value of pressure. Because if we were to, say, flip the momentum of this particle so it's going that way, but it's exactly the same size, this will give exactly the same pressure. So for every possible macrostate, there are a vast number of different microstates. And it's the macrostates that we're interested, because the microstates are directly unavailable to us. It might be useful to think of another example. Let's say we have a box of 100 coins, and each coin we can flip it and it's either heads or tails. So the microstate is giving a specific value for heads or tails for every single coin. So it's coin 1 is heads, coin 2 is tails, coin 3 is heads, coin 4 is heads, coin 5 is tails, coin 6 is tails, and so on. You have a specific value of heads or tails for every single coin in the box. And the number of different microstates is equal to 2 to the power of 100. That is a vast number of microstates. And it's like this because each coin has 2 possible states it can be in, heads or tails, and we need to multiply the number of states each coin has with every other coin in order to get the total number of states. And that's where we get this 2 to the power of 100 from. But a macrostate is saying what happens, well, one possible macrostate is 50 heads and 50 tails. And this is totally ambivalent about the order in which the heads and tails come. And you can see that there are a number of different microstates associated with this macrostate. So one microstate will be the first 50 coins are all heads and then the next 50 are all tails. Or another one will be the first one is tails and then the next 50 are heads and then the next 49 are tails, and so on. So there are a vast number of microstates associated with this macrostate. So that's the concept of microstates and macrostates. The microstate is the most granular information possible, and the macrostate are the macroscopic values for that system which we can measure, observe, interact with, all these kind of things. So now we need to move on to how this applies with our concept of temperature and what's going on here. Right, so now I've cleared some space on the board, and I've rewritten things a little bit here. So here we have body 1 and body 2, and instead of just saying the temperatures of the bodies, what I've used is a more fundamental concept, that of energy. So I say body 1 has energy E1, and body 2 has energy E2. And this omega 1 is the number of microstates which is compatible with body 1 having energy E1. So we say omega 1 as a function of E1. Now what does that mean? Well, we said a microstate is every possible arrangement of atoms. It defines the position and momentum of every atom in the system. So this omega 1 is all the possible microstates which are compatible with body 1 having energy E1. So the total energy of body 1 is E1, and for that there are a vast number of possible arrangements of the atoms within body 1, and the number of different arrangements there are is omega 1. And we say omega 1 is a function of E1, because if we change the energy, if we change E1 a little bit, then there's a whole different set of microstates which are now compatible with that new energy. So we have omega 1 as a function of E1, and likewise body 2 we say has an energy E2, and the number of microstates compatible with body 2 being at energy E2 is omega 2, and we say omega 2 is a function of E2 in exactly the same way. So now we have the total number of microstates of the conjoined system of E1 and E2. And that is equal to omega 1 multiplied by omega 2. And this is just like the example which we had for the coin tosses. We had 100 coins, and the number of different microstates for those is 2 to the power of 100. And we can see why that is here, right? Because for every possible microstate which body 1 is in, you can have the entire gamut of microstates that body 2 is in. And then we add all those up, right? So the total number of microstates of the conjoined system is omega 1 multiplied by omega 2. And omega 1 is a function of E1 and omega 2 is a function of E2. Now, we have to make a very important deduction at this point, and that deduction is based on some key assumptions. And what we're going to assume is this. We are going to assume that every microstate is equally likely, and we are going to assume that the dynamics of the system are such that the microstate is constantly changing, i.e. that the particles are always moving around, so you don't just get locked in one microstate, but things are moving, you're always changing microstate. And given enough time, a system will explore all possible microstates because all the particles keep moving around. Now, what can we deduce from those assumptions? Well, what we can deduce is that the macrostate that we will end up in is the one which maximizes the number of microstates associated with it. So let's think of a couple of examples of that, right? I'm standing in a room and there is a number of air molecules in this room. Now, a macrostate with a very low number of associated microstates would be something like all the air in this room spontaneously rushing up to the top corner. We never see that happen because there are very few arrangements of molecules in this room where that is the case. There are many more arrangements where the particles are relatively evenly distributed around. So the macrostate that we end up in is the one which has the greatest number of associated microstates with it. And I hope that kind of intuitively makes sense. Like, another example would be, we know that when we play the lottery, every individual sequence of numbers is equally likely to win, right? You could play 1, 2, 3, 4, 5, 6, 7 just as much as you could play 54, 33, 27, and so on, right? Every individual sequence of numbers is equally likely to win the lottery. But you're much less likely to win the lottery if all the numbers are under 10 than if, say, at least one number is greater than 10. Because there are many more combinations of numbers where one or more of them is greater than 10. So if you'd say, I'll win the lottery if I have all the combinations of numbers where at least one of them is bigger than 10, and you'll win the lottery if you have all the combinations of numbers where they're all under 10, then I'm much more likely to win, right? I'm in a macrostate with many more corresponding microstates. And that is the key deduction which we're going to use now, that the macrostate, once again, which we end up in, is the one with the most corresponding microstates associated with it. So let's apply that concept and do some maths with it, and then we'll arrive at a definition of temperature. Right, so I've got my notes with me in case I make a mistake. What we've said is that we want to maximize the number of possible microstates associated with our macrostate. And what that means in practice is we take this function, which is the function which determines the number of microstates our system has, and we differentiate it with respect to E1, the energy of body 1, and then we set that equal to 0. Now this is just calculus, which says that when the rate of change of something is 0, that's when you're at a maximum. So I'm not going to go over that, but feel free to look that up. And we could just as easily use E2. We could maximize this function with respect to E2 and set it to 0, and we get exactly the same result, but I've chosen E1 here. So we need to work out the maximum number of microstates. We need to work out where omega 1, omega 2 is a maximum, and we do that by differentiating with respect to E1 and setting that equal to 0. So let's do that. Let's work it through. So what we have first is we use the chain rule, which means we differentiate this first term and we hold this second term constant. So we hold the second term constant. We have omega 2, which is a function of E2. And then that's multiplied by the derivative of this first term, which is d omega 1, which is a function of E1 by dE1. And then we add, and this time we hold the first term constant, and we take the derivative of the second term. So we hold the omega 1 constant, we take that out the front, omega 1 E1. And now we do d omega 2, but since omega 2 is a function of E2 and not E1, we can only differentiate omega 2 with respect to E2. So we go by dE2. But to make this work, we have to add this second term, which is dE2 by dE1. Now, I'm not going to come up with a rigorous proof for that in this video. I mean, there's numbers of different ways to remember it. The way I used to remember it when I was at uni is that these DE2s cancel and this DE1 can move over there, and so it actually is sort of the same. That's not rigorous, of course, it's just a way of remembering it. Right, so this is our chain rule, and we have set that equal to 0, remember, here. So now we need to make one further observation, and that is that we have placed this conjoined system in thermal isolation, which means it cannot exchange heat with its surroundings. It cannot gain heat, it cannot lose heat overall. So the total energy of the system, written as capital E, and that's equal to the sum of the energy of body 1, E1, and body 2, E2. This does not change because this system is in thermal isolation. So therefore, dE is equal to 0. There is no change in energy over time, and dE is equal to dE1 plus dE2. So this tells us that dE1 is equal to minus dE2. And bear in mind, all this is saying is that any infinitesimal change of the total energy of the system, dE, is equal to the infinitesimal changes of the two bodies that make up the system. That's all this statement is saying. So dE1 is equal to minus dE2, or rather dE2 by dE1 is equal to minus 1. That's just rearranging. So now we're going to plug this into our formula up here. And bear with me because we're almost there. So I'm going to stop writing as a function of, because I think you'll get that. So I'm just going to write the omega 2s. So we have omega 2 d omega 1 by dE1. That's our first term, that's unchanged. And then we bring in a factor of minus 1 from this term over here. So instead of a plus, it's a minus. And then we have omega 1 and then d omega 2 by dE2. And that is equal to 0. Let me just check I've got all that right. Yes, I have. So let's rearrange this now. I'm going to bring this over on this side, and then I'm going to do it so we have one term which is only omega 1 and one term which is only omega 2. So I bring this over here and I divide both sides by omega 1, omega 2, and I end up with 1 over omega 1 d omega 1 by dE1 is equal to 1 over omega 2 d omega 2 by dE2. And if any of you have done advanced GCSE or A-level trigonometry, you'll know that this is equal to the derivative of ln of omega 1 by dE1. And this is equal to the derivative of ln of omega 2 by dE2. And again, this uses the chain rule, so feel free to take the derivative of omega 1 with respect to E1, and you should find that you get this. Now, what we've done here is we've said, let's look at the instance where we've maximized the number of microstates. And again, by our assumptions, that is the position where we expect our system to end up when it's in thermal equilibrium. However we start, by the end, we're going to end up in the macrostate with the greatest number of microstates. But what we also know from the beginning of this video is that thermal equilibrium occurs when the two bodies are at the same temperature. So it makes sense to identify these terms, this with body 1, this with body 2, as being related to the temperature. And that's exactly what we actually do. We define the temperature as saying 1 over kBT is equal to d ln the number of microstates by the energy. And okay, so what do we have here? Well, Kb is just the Boltzmann constant. That's a constant, you don't really need to worry about that. But you see that we have defined the temperature in relation to the rate of change of the microstates with respect to the energy. And this is a very rigorous definition of temperature, and importantly, this gives consequences and is testable. Now, this might seem very abstract, but I mean, we are studying physics. Abstract things are going to happen quite a lot. And it is abstract, but you can get a sense of what this definition of temperature is getting at. And as a very quick aside, remember we looked at Stirling's formula earlier, which deals with logarithms of very large numbers, and the number of microstates is vast. So you can see where Stirling's formula is going to come in handy in the future already. But coming back to this here, the temperature is inversely proportional to the rate of change of these microstates as we change the energy of our system. So I find it helpful often in these instances to look at some extreme cases. So what happens at zero temperature, at absolute zero? Well, at absolute zero, the energy of the system is absolutely zero, and there's only one way that that can really happen, right? None of the particles are moving at all. I mean, this is actually a theoretical impossibility, but let's just pretend it isn't. Let's just very, very low temperatures, right? If you make a if temperature is extremely low, then 1 over the temperature is extremely high. It's a very, very big number. So what that means is, if we make just a very small change to the energy of our system, if we take the energy of our system, not zero, but we just increase it a little bit, then we go from virtually zero microstates, which can have zero energy, to suddenly a lot of microstates that can have an energy a bit bigger than that. Because now we could have one particle whizzing over there, or we could have two particles moving slowly over there, or we could have three particles moving very slowly, or we could have one particle moving quickly but in a different place. So the rate of change of the number of microstates with energy is vast, because we've gone from a place at zero energy with no microstates to a place a little bit above zero energy with suddenly quite a lot of microstates. Conversely, if we look at infinite temperature, then 1 over infinite temperature is equal to 0, and that means that any small change of energy, at infinite temperature, doesn't lead to a great change in the number of microstates, because things are already moving at the speed of light. Things are already moving maximally, right? Changing the energy a tiny bit where you're already at infinite energy has very little impact on the number of total microstates associated with that energy. So hopefully that gives sort of a slightly intuitive idea of what this definition of temperature is getting at. But like I say, the important thing is that this has consequences and is testable, and we can apply it in our theory, and it's also in line with all of these observations we make and are intuitively obvious about temperature. It matches our experience, and it is usable in theory rather than being something vague. And this is what temperature is defined as in statistical mechanics. Right, that's a lot to take in. I think since we've talked about microstates and macrostates, there's another video I made actually on the nature of time, but it discusses entropy. And entropy is a function of microstates and macrostates. So as the next video in the daily physics playlist, I'll insert that video, and that gives another example of how to understand microstates and macrostates and entropy, although it doesn't use those terms. And then maybe we can talk about Boltzmann distributions, and we can actually get onto a rigorous definition for entropy as well. Look forward to seeing you soon.